Okay, hello. So let us now review a little bit of things and do some more examples. So do you remember we talked about sets and we learned about two concepts, membership and being a subset. Yes? So do you remember what was let me just review a little bit things here and then I clean and then I will start doing this. So if A belongs to A, it means that if you look inside the curly brackets around the set A, you will find exactly A as one of those elements. Yes, that's the meaning of membership. And then if I tell you that I have two sets, A and B, I would write A is a subset of B. What does this mean? It means that whatever I see as a member of A, it's also a member of B. That's the meaning of A being a subset of B. We use the Venn diagram to understand this a little bit better. So I told you, do you remember that was the convention that you draw a rectangular for the universal set? And then if I want to represent this using the Venn diagram, then what I do, for example, I can have this. Let me make it simple. So this is A, let me call this B, and then I have to respect the fact that A is supposed to be the subset of A, a subset of B, so I have to draw it inside B. And the reason that we put this equality is because we are emphasizing that every set is also a subset of itself, yes? And so in extreme cases, I would say the largest subset of a set is itself, and the smallest subset is the empty set. So now we'll realize that the empty set, the proof was short, but might be a little bit convoluted, so we use the proof by contradiction, so that the empty set is a subset of every set. So, and then we define this mathematically. This is optional if you want to just know. It means that for all possible values of x, possible x's, if x belongs to A, I can conclude that x belongs to B. And we also define what do we mean when we say that A is not a subset of B. Do you remember what was the definition? When you say that a set A is not a subset of B, it means that, yes?
There exist elements in A that are not in B.
Not elements, even one element is enough. There exists an element x such that x belongs to A, but or and x does not belong to B. Okay? And then there was another terminology we defined the notion of a proper subset. So what is the meaning of a proper subset? It means a subset which is not equal to the set itself. Yes, that's just the terminology. And in the books that they use this symbol for subset relation, we use this like a strict one. So when I use this in the exam or you see it in the book, it is telling you that not only A is a subset of B, but also A is not equal to B. But when I see this symbol, there is no guarantee that A is not equal to B. Might be that A is equal to B. If you want to draw an analogy to understand this better, for numbers we have these two symbols. A is smaller than B strictly, and when we say A is less than or equal B. And when I use this symbol, it means that there is a possibility that these two variables are equal. But when I use this symbol, it means that this is a strictly smaller than this. There is no chance of having. Even though this is sometimes a good analogy, but you shouldn't push this analogy so further than this, yes? They are not exactly the same. They are not enjoying the same properties. So one important difference between this and this symbol is what? Can you remember? There is a big important difference with this relation among numbers and this relation among sets. The reason that I'm talking about this, because somehow I also sometimes carelessly say the smallest set, the largest set, but this doesn't make sense. There is no smallest in the sense of a smaller in numbers. There is no largest in the sense of largest in numbers. But we're actually abusing these words, but you understand what I mean. So I just want you to, what is the main difference between this symbol, this relation, not symbol, this relation among numbers and that relation among sets. What's the main difference? Okay, so you don't remember. The main difference is that it doesn't matter if I choose any pair of real numbers, either this one is true or the other way around is true. If I ask you to choose two numbers, let's say A and B, either A is less than or equal to B or B is less than or equal to A. This is for sure. Is that understandable? But this is not the case for subsets. You can choose two sets so that neither A is a subset of B nor B is a subset of A. Yes, I think Dimitri gave me the example last time. Yes. So what was the simplest example? Actually, I remember your example. So you said that A, let us take A to be this, and let us take B to be this. If I ask you, is A is a subset of B? The answer is negative. If is B a subset of A, the answer is again negative. But this cannot happen with numbers, yes? If you choose any two real numbers that you like, either the first one is less than or equal to the other one, or the second one is less than or equal to the first one that you have chosen, yes? So that's a big difference between this and that. So it means that any two numbers are comparable. But this is not the case that I can compare any two sets. So this is why this relation gives you a nice way of ordering real numbers. Yes? So if I throw for you a bunch of real numbers, you can arrange them in increasing order. Or if you want to, you can arrange them in decreasing order. Yes? So you don't need to put this sign between. You can tell me that I want to arrange them in ascending order and then separate them by commas. But you cannot arrange sets in ascending order or descending order, something like that. Because there might be sets that are not comparable. If I say, do you think this set is smaller than this set or the other way around? Neither of them. Is that understandable? Yes? Okay. Now what else we had? I think that's it, more or less. We have these concepts. Okay, now I want to do some practice. So this kind of exercises are important to understand. I give you a set and I ask you to write down all the subsets of a set. Okay, I want to define something later. I have written it optional. It's not in the book, but it's not a hard subject, so I can just tell it to you. So let me just clean this and then do these exercises together, and then we'll come back to see what I want to define here for you. Okay. I want to solve the first example, so let me change my color. So I want to write down all the subsets of A. So let us review something. So what is the cardinality of this set? 2. One of them is A, the other one is the set including A. Yeah? So there are two elements in A, so the cardinality is 2. So do you remember what was the formula of the number of subsets? Yes, Dila?
2 to the power of number.
Yes. So here in this case, how many? 4. Yes. And then you always start with your list with the empty set, and you always end. Of course, this is not a have to. You can just arrange them whatever you like, but it's better to be organized. So if I want to list this, I would write the empty set. Okay. And then, for example, I don't know, let me just go below. Is it okay that I write A? No. You have, be careful. If you just write A, you will not get the point for this one. So you have to put the curly brackets. Let us check. Is this a subset of that one?
Yes.
Why? Because whatever is a member of this set, which is only one thing, and A, is also a member of this set, not because of this, because of the first one. Is that understandable? Okay. So this is one subset. Another subset, can you tell me? Curly brackets, again, curly brackets, and then A. Yes? So this would be curly brackets, A. And then the other one is the A itself. Yes, so if you don't mind, because there are no space, let me just write A itself. So these are the 4 possibilities that we can have, and as you predicted, there are exactly 4 of them. Is that understandable? So it's extremely important to be careful about how many pair of brackets you put. Okay, if that's wrong, you will lose the points for that part. Okay, so let us go to the next one. Okay, what is the cardinality of this set? It's 3, so I should have 2 to the 3, which is 8 subsets. And as usual, let me just write them here. So I start with the empty set, and then I go to 1 element subsets. What is the first one that I want to write here, do you think? Yeah, this would be a curly bracket open, B, and curly brackets closed. Yes, curly bracket closed. And then I go to the next one. So this would be curly bracket, again another curly bracket, and then this is closed. Yes? And then I go there, you should be careful. I need to open a curly bracket and put the whole package inside it. Is that right? So that's also another subset. But then, do I have more subsets? Yes, I need to consider 2 elements in each case. So I open a curly bracket here, I put these 2 inside. And then I open a curly bracket, I put this one and the last one inside. And then I open a curly bracket, I put these 2 inside. And then finally, I just write B. So 1, 2, 3, 4, 5, 6, 7, and 8 as predicted. Yes?
In order to calculate the combinations,
yes?
you take the factorial of number of elements divided by 2.
No. It's a coincidence here.
Oh, okay.
Yeah. It's a little bit more complicated than that. But yes, in this case, yes. Yeah. Okay. And then let us go to the other example. So there are 2 more sets here. Okay, so let me talk about M. So what is the cardinality of M? 1. Is it equal to the empty set? No, because this is a set containing the empty bag or something like that. So that is not the empty set. So how many subsets do you expect? No? 2, because this cardinality is 1, 2 to the 1 is 2, so there should be 2, and that's clear. What are they? The empty set and M itself. Yes? So these are the subsets. So here, what's the cardinality? 2, so how many do you expect? 4. Again, the first in the list is the empty set, the last in the list is your N. Then I will have something in between. Okay? So, what is the next coming? Set of the empty set. Yes? And the other one is the set of the empty set. These are the 4 ones. Is that understandable? Okay, so I don't think that's a hard thing, but be careful. For example, if I give you 2 points for this, even if you miss 1 curly bracket, you will lose the point for that. So, okay? So you need to be careful. What do I mean by what I wanted to define is something in set theory is called the power set. And this is natural, you know. Here I am writing them, I am just throwing these subsets on the board. But usually we can arrange them as elements of another set. That set is called the power set. Yes? So what do I mean? If I open a curly bracket here, and if I close the curly bracket here, then this set that you see here is called the power set of A. Okay? So what do I mean by the power set? So let me write it here. Let me define it here, then I will clean it. So let A be a set. The power set, this is optional. I want you to know, this is not hard. The power set of A is denoted by, you put a curly P and then you put A in front. is denoted by this, and it is defined as follows. Okay, sorry for this mess, but yeah, I have to write it here. So this power set is the set X, is the set containing all elements X such that X is a subset of A. So if I don't want to confuse you, you already know how to write the power set because you already told me how to write these things. What you need to do is to put them inside another set. That set is called the power set of the original set. Yes? For example, in this case, if I want you to calculate the power set of A, you open two bigger curly brackets here and there, and then you have already told me these. I put them one by one there. First I put the empty here, and then I put this there. Yes, then I put the other one there, and then I put A itself, and then I close this. As simple as that. So when you talk about the power set, it is a set so that all subsets belong to the power set. Yes, that's the meaning. So I don't think we need more examples, so just writing the power set. So what is the cardinality of the power set? So what is the cardinality of the power set of A? 4. No, in general. If I have a finite set A, you write a nice formula for the cardinality of the power set,
2 to the power of number of elements,
which is the cardinality of A. So this means 2 to the power of cardinality of A. So that's the formula. If you want to calculate the number of elements in the power set, you'd raise 2 to the power of the cardinality of the set itself, if the set is of course finite. Otherwise this doesn't make sense at all. Any questions so far? Okay. And if we can finalize this exercise safely, then it means that you have understood everything for membership and subset, I think. So let us see if that's true or not. Any questions regarding the power set? So emphasize, the power set is optional. It means that I will not ask questions using an example, okay? Okay, so let us now try to understand this. Try to understand this question to see which one is true, which one is false. I have given you 4 sets, A, B, C, and D, and I have given you some statements regarding membership and subset relation for these sets, and I am asking which one is true, which one is false. I think we can start doing it together. So what is the first statement, true or false? True. That is clearly true. 1 belongs to the set A. If you look at A, how many elements you see there? 3 elements. One of them is just 1, the other one is 2. The other one is the set of 1 and 2. These are the 3 elements. So is one of them exactly 1? The answer is yes. So this is true. What about 1 is a subset of A? False or true?
False.
True or false?
It's false. It's false.
Yes, false. Because subset is defined for 2 sets. When you use this symbol, what do you expect to have on the right hand side? What do you expect to have on the right hand side? What do you expect? Do you expect to have a number on the other side?
No.
You expect to have a set on the right hand side, and you expect to have a set on the left hand side. Yes? So here A is of course a set, but 1 is just a number, it's not a set. So this is actually meaningless. So we say false. What about the third one? It's also false, agree? Because if it is going to be true, it means that one of these 3 elements should be exactly this, which is not the case, so it's also false. So that one, B is this set, belongs to A. True or false? Be careful, do not spoil the example, okay? I don't have any other examples. I want you to understand. I want you to understand this. Think about this one and this one together. You want to answer?
Yeah.
Okay, so the B belongs to A, true or false?
That should be false.
B a subset of A, true or false?
True.
Yes, true.
Is it true?
Yes.
Yes. So this is false, this is true. Yes? Why is that? If B is going to belong to A, what is B? B is this package. If you go inside A, do you see this as a member? No. It has an extra pair of curly brackets. So B belongs to A is a false statement. Questions? Yes?
But if, let's say, it inside of A, it had an extra pair of
That was
brackets,
right.
then it would be true, right?
Yes. Yes? Questions? Everybody agrees that this statement is false? B belongs to A is false?
Yes.
So B is a subset of A, true or false? True or false? It is true. Why? Because when you talk about subsets, you need to look inside the first one and inside the second one. Yes? If I go inside B, how many elements I see inside B? 1, and this is this package now. If I ask you what is an element of B, this is an element of B. So this is the only element of B, which is also an element of A. So whatever is an element of B is also an element of A, so that is true. Questions? Understandable?
Yes.
Happy or not? Okay, so you need to laugh, okay? So, because you're frowning, yes? So that is a little bit misguiding for you. So 1 belongs to B. False or true? It's false, yes? Because the only element of B is this guy, which is not this one. So it is easy to detect that this is false. So let me put these two in a box to compare something later. Okay, let us go back to this question here. C is a subset of B.
False.
It's false. Yes? C is a subset of B. If this is going to be true, it means whatever is inside C should also be inside B. What are inside C? 1 and 2. Is one of them in B? None of them is actually in B. Neither 1 is in B, nor 2 is in B. So this is clearly false. What about C belongs to B?
True.
True or false?
True.
Don't hesitate to say. You can save my breath. I'm tired. Okay. True or false?
True.
True. Okay. So this is true. If you have questions, let me know. Okay. So let me. I unfortunately I wrote them in the wrong order. Here, membership was false. Subsetship was T. Yes. Here, membership was true. Subsetship was F. So I just want to tell you that both cases can happen. Yes? Is that understandable? You see here, membership was false. So I gave you an example for which membership is false, but being subset is true. And then I simultaneously give you an example this time that membership is true. It was false here. Being subset was false. So that's also possible. Let us continue forward here. C is a subset of A. True or false?
True.
It's true. Because of which one? Because of this 1 and 2 or this 1 and 2?
First one and two.
First 1 and 2. Exactly. Because you see the elements inside C are 1 and 2 and you see them here. So that is true. And then C belongs to A. True or false?
True.
Again true. Yes. So because of which one? Because of this 1 and 2. Yes. So now you see that membership is true. Being a subset is also true. Yes. Let us go here. Set of 1, singleton 1 belongs to D. Is true or false?
True.
It's true. What is the other one? This is false. Yes? And now you see the other way around can also happen. So there is no very strict thing that we can go. Everything can happen actually. Okay, let us do this very quickly now. What about this one?
True.
This is true. This is false. Yes? Is that okay? Okay, so you see that this is not hard, but you need to pay attention and be careful. Now let me ask you some questions. I just want you to know about these names. A relation is called reflexive. You don't need to memorize them, but I just want you to know. This is optional, but you need to be able to answer my questions. This is not optional. Okay? So a relation is called reflexive if every element is in relation with itself. Okay? For example, this relation for numbers is reflexive. Why? Because every number has this relation with itself. Any number is smaller than or equal to itself. So this means that this relation is a reflexive relation. Is that right? Yes? So, a friendship, do you think friendship is a reflexive relation? I don't know if you are a friend of yourself. That is the meaning. If everyone is a friend of himself or herself, this means friendship in the set of humans is a reflexive relation. Yes? But the famous relation that is reflexive is being a classmate or being in the same class. So everyone is in the same class as himself or herself. So being a classmate is a reflexive relation among humans. Okay? Now another relation is called symmetric relation. A relation is called symmetric if A is related to B, B also is related to A with that relation. Yes? So the classmate relation is symmetric. Do you agree? Because if, I don't know, if Carl is a classmate of Dennis, Dennis is also a classmate of Carl. So this is a reflexive. Let me ask you one question. Brotherhood, is it reflexive relation? Yes?
No.
Why?
Because a brother can be a brother to a sister, but
Sister,
a sister
yes.
is not a
So if
brother.
I am, for example, the brother to my sister, I am her brother, but the other way around is no. I am her brother, but she is not my brother. Okay, so brotherhood is not a reflexive relation. Is not a symmetric relation. And one important thing is called a transitive relation. A transitive relation is that if, for example, this is also is this relation symmetric or not? Symmetric means that if the first one is related to the second one with some relation, the second one is also related to the first one by the same relation. Yes? This is not symmetric because it might, so if 1 is less than or equal to 2 is true. Yes? But 2 is less than or equal to 1 is false. So there is no guarantee. So this relation is not symmetric. But this relation is reflexive for the reason that I told you. It has another property which is called transitivity. So it is transitive. What does it mean? It means that if A is less than or equal to B, and simultaneously this B is less than or equal to C, what is the conclusion coming out of it? A is less than or equal to C. If a relation holds this property, that relation is called transitive. You don't need to know the words, but it is good to know about these properties, okay? So A is less than or equal to C. So this relation was reflexive, this relation is transitive. Now let me just play around with these words, okay? So is being a classmate transitive? Classmate in the set of humans. Is a classmate a transitive relation?
No.
Yes or no?
No. You can be different classes.
So it wouldn't be possible.
If I'm classmate with Kevin and he's classmate with someone else, he can be two classes.
Okay, so you confuse me. But classmate is actually so being in the same classroom. I mean,
Okay, then yes.
this is the weak people. So in that case, it's a transitive. Yes, because if you are sitting in the same classroom as Kevin and Kevin is the same classroom as Ruben, so definitely you are the same classroom as Ruben. So if you consider this in this case, this relation is transitive. Now my question for you. This subset, being a subset, is a relation among sets. Yes, my question, is it reflexive? How do you translate this question? It means that, is it true that every set is a subset of itself? Being reflexive means every element should be in relation with itself, according to that relation. This relation, I am concentrating on being a subset as my relation. Is a subset, is a transitive, is a reflexive relation or not? Yes?
Yes, it is.
Because every set is a subset of itself.
Yes.
Is this relation symmetric? No. The answer is no, because it might happen that A is a subset of B, but B is not a subset of A. This can happen. Now the question which I want you to write down, is it transitive or not? What is the meaning of this sentence? I am asking you, is this relation transitive? I am asking you, if A is a subset of B and B is a subset of C, can I conclude what? Do you understand that? So forget about the name. If you don't like the name transitive, whatever, forget about them. But I'm asking you, if I tell you that this is true, and if I tell you that this is true simultaneously, can I still conclude that this is true or not? If the answer to this is yes, then it means this relation is a transitive relation. If you don't like, you can just forget the name. Okay. Is it true or false? You can also imagine it using Venn diagram. Okay, by Venn diagram, is it true or false?
True.
Yeah, by Venn diagram, it seems obvious, yes? Because you say that A is a subset of B. So let me draw a Venn diagram for you to see what's going on. But of course, Venn diagram is not a mathematical proof. It motivates you towards the right direction, but finally you need to give me logics. So A is a subset of B. So this means that if this is A, so B is something like this, containing the whole A. And now forget about A. There is another set so that B is a subset of C. So how should I draw C? I need to draw C in a way to contain B, which automatically contains A. So it means that yes, it seems true that A is a subset of C. So you might think that I am exaggerating it, but let me ask you another question. Is membership transitive? What is the meaning of membership being transitive? It means that if A belongs to B, if a set belongs to B, and this set itself belongs to C, can I conclude that A also belongs to C? So you see, this is a question mark for my relation of membership. This is the same question mark for my relation as being a subset. Intuitively, using this picture, we think that this must be true, even though we haven't proven it yet. But what do you think about this? If you think this is true, you need to tell me how to prove it. If you want to tell me this is false, what you need to do is a counterexample. Bring a counterexample. So if you want to prove, it doesn't matter even you bring me 1 million examples which work. You need to give me the statement, the argument why this is true. But if you want to refute something, if you come up with just one single example, you are actually able to refute that thing. And this example has a particular name in mathematics. It's called a counterexample. Yes? Okay. So now, Intuitively, we think this is correct. What about this one? Okay, are you against it or for it?
Against.
Against. So then can you give me an example?
Yes, so let's say A.
The simplest, cook up the simplest possible example.
A is 1.
You mean this?
Actually, I think it can be just 1. Not a subset, just not a set, just 1.
Okay.
Then B is a set containing 1, and C is a set containing B. Yeah.
Something like that.
Yeah.
Yes? So A belongs to B is true. B belongs to C is true, but A belongs to C is false. For example, I am a member of Sweden. Sweden is a member of United Nations, but I am not a member of the United Nations. Yes, apparently. Unless I have a secret job, yes? Okay, so this is something, so be careful. This membership is not transitive, but being a subset is transitive. Is that clear? Yes or no? Okay. Let us see. By the way, do you remember the famous sets in mathematics? By the way, why this is true through logic? It's also very important. Let me prove it. The proof of this is probably an exercise in the book, but I want you to remember it. Because if you want to work algebra so when you remember things about numbers in the algebra, in arithmetic, you also need to remember relations there in algebra of sets. So why this is true? Might be this should be an exercise in the book. You want to bring me the good argument. This was, of course, Venn diagram. This is not a proof. It's just a motivation behind why this might be true. But why this is true? This is important. This is a very simple exercise, but I want to go through it. What is my goal here? How many assumptions? I want to prove this statement. I have two assumptions, and I want to prove one statement. What is the statement that I want to prove? Can you just read it for me? What is the which one is the statement that I want to prove? Yes?
Everything in A is...
This one. A is a subset of C. What are my assumptions? How many assumptions do I have? Two. One of them is that A is a subset of B, and the other one is B is a subset of C. This is the things that I know. This is the thing that I want to show. Now, what you said is correct. If I want to show this, what I am supposed to show? I have to show that everything in A is also in C. How should I start? I would say that let X be, so let me write like this, X be in A. Do I know what is X? No, I am just telling you that let me take one element from A, let me call it X. I show that this X belongs to C, then I am done. Agree? I show that, you don't need to write it down, but to emphasize, I show that X belongs to C. If I can show this, then I am done. Agree? This is the way that you need to learn, because Mathematics 5, you need to be able to write things properly. Okay, now I start from here. X belongs to A, and you told me that A is a subset of B. Comparing these two, what is the immediate consequence of this based on the definition of being a subset? What can I conclude, everyone? X belongs to B. Agree, everyone, or not?
Yes.
Okay, so you see I started from this assumption. I used one piece of your assumptions. Together I got this. Now that I got this, I have another piece of information you provided for me, and that is B is a subset of C. What is the consequence of this comparison? X belongs to C. What was my goal? So I am done. Is that understandable? So you need to learn how to write it down. Okay. So we have these properties. So if I want to emphasize the main points of this, one of them is that empty set is a subset of every set. The second one is that every set is also a subset of itself. The third one is that if A is a subset of B and B is a subset of C, if you want to, you can conclude that A is a subset of C. I think this is important to at least remember these facts. Okay. And now there are some famous, yes?
1, 2, 3.
Yeah, it's one.
Yeah, one more.
Okay. Yes. Is it really? Okay, so yeah. 2 is, yeah.
So it's enough to show that X belongs to A for all sets. It's enough to show that X belongs to A to show that it will always be true for all types of sets.
Yes. Because what I am saying is that I would say let X, if you want to be very pedantic, I would say that let X be an arbitrary element of A. I do not say arbitrary. So it means that this kind of argument is valid for any X that you like.
Yes.
And we are done. Yes. But we don't, usually in mathematics text you don't see arbitrary things. So we say that let X be an element of A. I try to show that this particular X belongs to C, but this reasoning goes for, you see, in this kind of reasoning, the name of this is not important at all. So I can repeat this process for all
Yeah,
X's.
but if A has more elements, you don't need to show that. That's just enough to show that.
No. This is considering even the cases that A have more than one element. I'm not saying that A has one element and that is X. I am saying that there is a set, let me pick one of these elements, say it is X.
Okay.
And for this X, I show it is in C.
Yes.
If you want to go to another one, but the same reason will go on. This is the reason. Yes, thank you. Okay, now let me just mention this because this is also in the book. There are some famous sets in mathematics. Probably the first one, is N. So I started from 1, okay? And then we have a set Z, and then we have a set of rational numbers, and then we have a set of irrational numbers, and then I have a set of real numbers, and then might be you have studied a little bit about the set of complex numbers, but we can leave this aside for a while. What is a relation between N and Z? Is it okay to write N belongs to Z, or is it okay to write N is a subset of Z, or none of them, or both of them? Subset is the correct way of writing. You agree? So this is wrong, but this is correct. Yes? So, and then what is the relation between Z and Q? Yes?
The same.
The same. This is subset. Every integer is automatically a rational number. Why? For example, why do you think -3 is a rational number? Yes?
You can divide it by 1.
Yes, -3 is another name for -3 over 1. And what is the set of rational numbers? What number is called a rational? A number which is in the form of a fraction such that A is in Z and B is also in Z and B is not 0. So if you have a fraction with these three properties, that number is called a rational number. So this is why Z itself is also a subset of Q. But do you know what is irrational? What do we mean by irrational number? Yes?
Isn't that number that you can't describe by...
Yes. If a number is not rational, it is called irrational. It might happen that all the numbers are rational, but this is not the case. The most famous one is the square root of 2. It is not rational. So it means that this will actually be interrupted. I cannot compare these two. You will see how is the relation between these two. But this is also a subset of R, and if you want to, this is also a subset of C. So I is something that we talk about later. So that is called the complement of this. So this is something that you need to know for this set. So yes, that's okay. I haven't. Let me see what is left to talk about. So I think more or less I don't want to continue more. because I want to give you to solve the problems yourself. Let me make sure. Okay, let me talk about something else. Okay, something that I want to talk, and that is the last thing that I want to teach you now, and that is the notion of an interval. Okay, so for some reason, I don't know why they haven't talked about intervals so far, but let me just talk about this and then we are finished. This is just the terminology. Okay, so this is the last thing that we want to talk today. So an interval, what does it mean, an interval? So let A and B belongs to R. These are two numbers, and let A be smaller than B. Okay? And consider this set, the set X of all those numbers such that X belongs to X belongs to R more than that, and X is between A and B. These kind of sets are so ubiquitous in mathematics, algebra, solving equations and things like that, that they deserve a particular name. Okay? If I want to draw a picture for you to understand this graphically, so assume that this is your x-axis, this is the set of real numbers. A is a real number, so let us say that A is here, B is here. This tells you that the set of all x's which are real numbers and lie between A and B. So what does it mean? If I want to draw a picture for you, this would be here. So yeah, this part is this interval. But it doesn't include A. To show that it does not include A, you put a hollow circle. It means that A is being excluded. And then you put a hollow circle here as well. It means that B is also excluded. So this set is called an interval. Yes? And then there is a symbol for that. And this is a little bit unfortunate. The symbol that we use is exactly the same symbol as we use for points with coordinates A and B, but they are quite different. So you need to understand them from the context. And there is another name for this. This is called an open interval. Open interval. So it means that you do not restrict yourself, so that's open. You can just move around. So that is called an open interval. This is just a name. Yes?
What if one is filled up?
Yeah, I tell you. There is no name. I will tell you. For example, if you have this situation, you put a bracket for A, and then you put B, and then put this. This means that this is included, this is excluded. Okay? So this means that the set of all X belongs such that X belongs to R, and A is less than or equal to X less than B. So if I want to draw the picture corresponding to that, then so it's for example, here is A, here is B, and then you make a filled point. It means that A is being contained, and then you exclude the last point. This is called semi-open or semi-closed. It doesn't matter. Of course, let me just skip this one. You can do the other way around. You can put brackets, so this parenthesis here and a square brackets there. Then then this would be the hollow one. This would be the filled one. You can have both of them square brackets, and that is called the closed interval. Okay? So if that is the case, you might have this scenario. Then this means that the set, this is and. I don't know why. This X belongs to R, and a is less than or equal to x less than or equal to b, if you want to draw the picture, you need to feed it both ends. So this is called a closed interval. Okay? How many intervals you see? 4. 1, 2, 1 that I skipped, 3, this one 4. So we have 4 intervals, yes? These are called bounded intervals. Bounded. It's clear, it's bounded from both sides. It cannot be larger than this, it cannot be smaller than that. They are bounded. Okay? But we also have unbounded intervals. It means that we start from one point, either go to infinity from the right or go to infinity from the left. Those are called unbounded intervals. Okay? And then I want you to tell what is the symbol. So, for example, you can consider this set. The set of x such that x belongs to R and x is greater than A. So if you want to show it, you put a a parenthesis for this, and you go up to infinity, and then you put this. Yes? I don't know. For example, what is the meaning of this? Can you tell me? What is the meaning of this? Yes?
That it can also be equal to
To A. Okay? We can also have this. We can also have this. Yes? Agree? So this means that strictly smaller than A. This means that less than or equal to A. Okay? So if you want to write it as a set, you write it without the notion of this symbol, without mentioning this symbol. But if you want to write it using this notation, you have to use these infinities. Yes? And infinity is always with this parenthesis, because infinity is not a number that can be achieved. Is that understandable? Yes or no?
Yes.
Okay. So this is something that you need to know. These are famous, so ubiquitous, so we give them a name. This is called an open interval. This is called a closed interval. Okay? I do not want to teach more, but we have a little bit of time. So what do you think we should do? We can talk a little bit about infinite sets. Okay? It's a little bit counterintuitive, and very interesting things can happen when you are dealing with infinite sets. So if someone asks you, is this a true statement or a false statement, what do you say? Yes? It's a false statement, because I just mentioned infinity is a symbol which represents a behavior rather than a number. Yes? In positive infinity means large. If I say here is infinity, you should say no, there is something more. If I say here is infinity, you should say there is something more. So that's actually a behavior. But there is some counterintuitive things that can happen. Even mathematicians, actually George Cantor, who started inventing the set theory, when I talked a little bit before, you remember, he also started thinking about this idea that the notion of infinity is a little bit strange in mathematics. Okay? And then I just want to try to convince you what strange things can happen. So what Cantor was actually facing to systematize the notion of infinity in mathematics. Okay, let me ask you something. If I ask you what is the cardinality of the set of natural numbers, what is the answer? It's infinite, so it's an infinite set. Okay, and if I ask you what's the cardinality of the set of integers, including the negative ones as well, of course, but that's also what? Infinite. But are they equal in size? Yes, so are they equal in size? Is one of them bigger than the other one? Because I cannot count. If you give me finitely many pens in one bag and finitely many pens in the other bag, I can count them and count the other one and see that which one is bigger. But that notion definitely does not work here, because no matter how much time you put on it, so you will not be able to finish counting the numbers in n and finish the counting the numbers in z and then compare them. Yes?
I think you can say they're both infinitely big,
Mm-hmm.
but they have different complexity.
So then you need to be very clear about the word complexity and your definition of being complex. Because intuitively we think that the number of elements in Z should be somehow double the number of elements in N. Okay? But very nice comparison shows that no, they are of the same size. Okay, this might be a little bit disturbing. This is what I'm saying, that when you want to deal with infinities, you need to be careful what you're doing. The number of elements, of course, for Z it might be a little bit difficult. Let me give you another example. So let me list all numbers here. All natural numbers here. I don't know, I have actually forgetting my counting these days. Okay, 5, 6, etc., etc. Yes? And then let me write only the even numbers below. So I would write 2, 4, 6, 8, and then 10, 12, etc. How many numbers you see in the first row? Infinity. How many numbers you see in the second row? Infinity. Here I am just selecting 1/2 of the list above, yes? I am just throwing away the odd ones and I am just keeping the even ones. But now I am asking you the same question. Which infinity is bigger than the other infinity apparently? Yes? Yes?
The one below.
The one below is bigger? It has more numbers, you mean? I'm not calculating the size of each element. I am calculating the elements. How many elements you see here and how many elements you see there. Yes?
I mean, it seems like the cardinality of the set above is bigger,
Yes.
because it includes all the elements in between.
Yes, this is probably the first natural thing comes to mind, but they have yes?
Can you say that the set above is less limited?
No?
Okay, that was it.
Yes? Yes?
I have a question. Is it because they are not both finite, and therefore you cannot say that the one over is much bigger than the one below?
Yes, because we cannot count them. But then the contour was facing this problem. Can I still compare the sizes without counting them? In reality it's possible. So for example, if I have a bag with some number of marbles in it and another bag with some other number of marbles in it. If I want to see if they have the same number of marbles in them, one way of course is to throw them away, count them and compare them. But there is another way. What might be you have been using it sometimes. I put my hands in both of them, take one from here and put it aside. I'm not counting. I am corresponding marbles together. Then I put my hands again and I pick one more and put them here. Okay? If it continues until nothing is left here and nothing left here, then I haven't counted the number of elements, but I am sure that the number of elements are the same. Let me give you another example. I don't know how many chairs are in this room. Might be there is a bunch of the students outside. I haven't counted the numbers. Yes? But I ask the students go and take one chair and sit on that chair. And after this is settled down, I come in and I see that all the chairs are filled with exactly one student. What is the conclusion about the number of chairs and the number of students? They are the same. Did I do any counting? No. So Cantor actually realized that the counting process is a dead end because I cannot count them, but I can take them away in pairs. Yes. For example, I take this one, I take that one, I take that one. Yes, I take that one. So it means that they have to be the same. If you don't believe it, let me tell you in a different way. Assume that you have the aula. infinitely big aula, each chair is numbered with one of these numbers above. Chair number 1, 2, 3, 4, up to infinity, okay? And now there are infinitely many students outside the aula, and then I want to let them in to sit in one chair, okay? I give them a number. The first student, I give that student number 2. The second student, I give it 4. The next student, I give it 6. And I tell them, look, because we are too much, please follow this rule. Divide your number by 2 and sit on that chair. Okay? So the first person who received number 2 divides it by 2, it becomes 1, goes into the aula and find chair number 1 and sit there. Okay? Number 4 divides it by 2, it becomes 2, goes and find chair number 2 and sits there. Now, of course, this will never end because there are infinitely many students, but forget about this part. And after it is settled down, I come in. Do you think I will have a student without any chair? Or will I have a chair without a student? Or will I have a chair with 2 students occupying it, fighting over it? Do you understand? It's nothing. So which student is sitting on chair 500? Is chair 500 filled?
Yes.
With who? Number 1000. Are 2 students are fighting for chair number 500 if they are following the rule? No. So the chair number 500 is filled with exactly 1 student. Okay? And the other way around. So it means that after you follow this rule, all the chairs will be filled up with exactly 1 student. It means that they have to be of the same size, even though it was very, very strange in the beginning. Is that understandable? So when you work with infinity, you need to be very, very careful. Okay, let me ask you another question. How many points are there in this line segment? How many points are there? Infinitely many points, yes? I have infinitely many points in this line segment. And I draw you another line segment. Yes? How many points are there? Which one contains more points? Yes?
So applying the logic you had before, they are, I mean, equal in yeah, I believe they are equal in size.
No, believe or you feel. Because believe should come, of course, I don't know if you believe in God without reason, I don't know, but believe should come after a reason.
I mean, you can apply the same logic, like for a point on one line.
No, it should be very clear. The logic is, that is what I am demanding. Either you don't believe that they are of the same, they contain the same number of points, or you believe in it. If you believe in it, exactly the way that I cook up the recipe for the students, I didn't say that I feel you can find the place, go in, then you immediately believe that that would be a mess there. I need to organize them. I might happen that I can have another way of organizing, that's okay. But I need to show that this is really organized. Meaning that by this rule that I am setting up, every chair is filled with exactly 1 student. I am not saying that the way that I assign the students is unique. But I found one way. If you find another way, you need to defend yourself. So when you say the number of points here and the number of points here are the same, you need to cook up a recipe that assigns exactly 1 point from here to this point and the other way around. I'm just hearing from you or others if you can have that rule in your head. Is the question clear? Yes, Jonathan? Do you have any idea?
Well, for example, if we do the same thing we did last time, we can say that the first line segment say that is equal from 0 to 1.
Mm-hmm.
And the second line segment is from 1 or 0 to 3.
Mm-hmm.
Then you just you get one number, and then you divide it by 3, and then you get placed on another one.
Okay, but what happens for the points in between? Because between 0 and 1 there are infinitely many points.
Yes. So
by the way, let me ask you a question. How many points are there
infinitely many.
Okay, is this infinity larger than the infinity of natural numbers, or it should be the same? No. It is much bigger. Why is that? It's a little bit confusing, I agree, but it's good. I'm not going to ask you these questions in the exam, but it is good to understand that what will happen, you have to follow pure logic. Otherwise, you cannot feel it. Because your brain is going to resist all the time. This is not the case, this is not the case. Is that understandable? So let me talk about R, the set of real numbers and the set of natural numbers. Both of them are infinite. Which one is larger, and why do you think it's the case? What is the idea? I don't want to prove it, but I am telling you. Okay, Elias.
Well, in R, you can also have 0.1, but you can always add a 0 to 0.1 or 0.0.
So which one is bigger? You are saying?
Well, the set of R.
The set of R is definitely bigger because of what? Intuitively, from 1, can I ask what is the next natural number after 1?
Yes.
Yes, I can, and that is 2. Can I ask what is the next real number after 1? I cannot ask. Because between any two real numbers, there are still infinitely many more. So it is intuitively seems clear that the number of elements in R is larger than the number of elements in N, even though both of them are infinities. But we can order infinities. Okay, something like that. Okay, but if I want to cook up this recipe, can you come up with an idea why these are the same? I will tell you like this. I will tell you that take this point, take your ruler, and take this point and put your ruler here and draw this line. Okay? I do the same thing with these 2 points. What happens? Let me just do it carefully. So what happens if I do that? So I will put it here and draw this line. So now I want to wait again. Now do you understand what's going on? And now let me clean this. Okay, let me tell you something. I take this one with this one and take them away in your head. So this is assigned to this. This point is assigned to this. So far so good. So I took one point corresponding it with this one, and I took this point associated with this point. Now I take this point away from this one, this point away, and that point away. Okay? Now I want to assign a point to this point. How should I do that? Yes, I will take this ruler again, put it here, and then I will draw this line, and then it will definitely intersect this point, this line at the line. I will say that, okay, I will cross this one with this one, go away. Okay? And now I will try take this one, for example. What should I do? I will again take this one and this one. And then connect them together. Okay, go away. Yes? So do you think that this process will collapse somewhere? Yes or no? For example, when this guy is going away, this guy is going away with which guy? With this guy. Yes? This guy and this guy are gone. So you can immediately feel that this process can follow very nicely. Yes? So if I choose this guy, I will take this one and say that you should go. And I take these two should go. These two should go. So it means that for every point on this line, I associated one single point from this line. So which point of this? Because when you say that the number of points here is more, it means that you can find a point without any partner here. Which point is that? Which point do you think I can imagine without a partner here? Can you imagine?
No.
So even if you say this, I just connect this one with here, then it will intersect somewhere here. So that is the partner of this guy. So you were feeling that this should include more points, but this is not in reality. You see, for every point here, I exactly associate one single point from here. And for every point here, I associated one single point from here. So you have to admit that they contain exactly the same number of points. If you don't admit that, you need to show me which point is without any partner. And this doesn't work. You understand me? Yes or no? So the number of points in this shorter one is exactly the same number of points in the other one, because when you are dealing with infinities. So that's a very, very nice example. Are you ready for another example? This, I was very excited and I couldn't believe when I was at your age. Let me just tell you something. Let me finish this one, then we can talk. Okay? Another example. So assume that. So the clock is 11:59. Yes. And now let us make it like horror movies. Now, strange things usually in horror movies happen at 12 o'clock midnight, yes? So now let us see. Let me have my stopwatch or whatever. How many minutes are from here to here? 1 minute. So let me call this one 0, and then this one is 1 minute. So the length that I want to do this experiment that I'm going to describe takes only 1 minute of your life. Okay? But let us see what happens. I have a very large, infinitely large bag here, and infinitely many marbles here. One of them is 1, the other one 2. I've given them labels. 1, 2, 3, 4, etc., etc. When the time is here, what I do, I will take the first 10 from 1 to 10, and I put it in the bag. Listen. Without any, of course this is not possible in physical reality, but you can imagine. I take number 1 to 10, put it in the bag, and throw number 10 away. Yes? Okay? Don't be scared, okay? Nothing will happen. So, here. And then you go here. Because by the way, this poor clock doesn't care about what's happening to you. It's just ticking, you know? So, it goes and reaches to the midpoint. Okay, so things are getting more exciting. So here, what you do, when the clock is here, you take number 11 up to 20, put it in the bag. This time you throw 20 away. Okay, is that correct? Okay, so here you throw 10 away, here you throw 20 away. Yes, and now this clock is again continue ticking, but when it comes to the midpoint, again, what you do, you take number, what was that? Number 21 to 30, put it in the bag, throw 30 away. Okay, so what's happening? You have to do it so fast because it is not possible. And then the next time you have even less time to do it. So probably you will convert yourself to energy, but forget about those things. Assume that you are doing it so fast. Yes? Now, this clock will actually reaches to this time because it doesn't care about what's happening to you, okay? And now my question is that when the time is exactly midnight, how many marbles are in this bag? It seems to be infinite. Yes? Why can you just give a reason to convince people, yes, there should be infinite? Yes?
Well, between 0 and 1, you can divide by 2 infinitely many times.
Yes? Yes?
Therefore,
so which numbers are not in the bag?
well,
Which numbers are not in the bag when
20, 30.
multiples of 10 are thrown away? Okay? So all these are in the bag except the multiples of 10. Okay? So there are left infinitely many. But let me change the experiment. It is very strange. It's really counterintuitive. I start the experiment again after I have been relaxed, probably tomorrow. And then what I do, I will take first to 10 to the bag. This time I do not throw 10 away. I throw 1 away. Okay? And then the second time, I put 11 to 20 in the bag. I do not throw 20 away. I threw number 2 away. Yes? What I am doing, compare it with the previous experiment. Each time I put 10 in the bag, throw 1 away. Yes? This time I am doing the same, but I have changed my mind from number 10 to number 1, from number 20 to number 2, and now again we reach to this point. How many marbles are in the bag? Zero. Yes? There are 0 marbles left in the bag now. It's really strange and counterintuitive, isn't it? Because your brain is still resisting. No, because every time I am putting 10, throwing 1 away, how is that possible? The first scenario I am ending with infinitely many marbles. In the second scenario I'm infinitely with 0 marbles in the bag. So be careful about when you are working with infinities. But can you understand why?
No.
It's easy. Let me ask you. No, logically it is easy. Even if I tell you the logic, your brain is still resist, and you will not believe me. And when you are going out, you say that this guy is crazy. Okay? But if you just follow the logic, you have to admit that. Let me ask you something. Is number 1 in the bag when we reach here? No. Number 1 is not in the bag because it was thrown here. It was thrown out from. Is number 2 in the bag? No. When was it thrown away? Here. Is number 3 in the bag? No, it was thrown here. Is number 4 in the bag? No, it was thrown here. Is number 5 thrown? No, nothing is there. Is that understandable? Okay, so enjoy your life now. So, the take-home lesson is that when it comes to infinity, be more careful and have respect for George Cantor. Yeah, but think about it.